Okay, so we are doing matrix factorizations today. We're skipping partitioned matrices because my class isn't covering it, and I really, as much as I would like to go over everything, it's not realistic. But this one's actually pretty interesting, and this book I've briefly read through it, and it kind of explains why it makes solving linear systems of the form ax equal b faster, but it doesn't actually say what it needs to say. And the truth is, to just solve via normal row reduction, ax equal to b, it's O of n3. Now, computing LU is also O of n3, but once you have them, to solve LUX equal to B, it's 2n squared. So you actually get an n squared algorithm out of it. So that is actually why we do this. And it's kind of weird to me. You know, I've seen this all over the place just from doing numerical linear algebra. Not that I really looked into it, but even the Wikipedia article does not say what it needs to say. It says computers usually solve square linear systems using LU. It's a key step when inverting a matrix. It's, you know, but what, and then you get this definition, you get all this crap, you get an example, but nowhere in here are you getting time complexities. And I don't know if, I don't know why. There we go. Way, way, way down. Oh, interesting. If two matrices of order n, I'm guessing that's just the size. What is the order of a matrix? I don't even know what that means. Can be multiplied in m of n. They really don't even need to say this. Well, maybe they do. I don't know if they need to or not. Then an LU decomposition can be computed in O of mn. So technically, you can compute the LU here, but for all reasonable things, we use row reduction and we get an n3 in the compute. Okay, here we go. Are we gonna get time complexity, man? I mean, this is just ridiculous, dude. It's really whatever. I'm not gonna get hung up on it, but I think it is a little bit strange that nobody talks about this. So there is a threshold when it's worth it to do the LU. But if I'm only solving a single AX equal to B, then maybe I should just do normal row reduction on the augmented A, B. In a nutshell, LU decomposition turns the costly O of n3 work of Gaussian elimination into a one-time factorization, which after every solve is dramatically cheaper. So if you only ever need to solve one AX equal B, just doing Gaussian elimination is fine. In fact, that process is exactly what you're doing when you form the LU. You just don't store the, well, but also you don't need to pay the 2n squared cost of computing Ly equal to b and ux equal to y when doing direct. Oh, yeah, I mean, you could just do this, right? If you have m different b vectors, elimination still does one big. So you don't actually. Yeah, I mean, okay, all right. I think I get it. The You just want to store the decomposition because later you're going to want to use it. But you could just as well, let's say you have a bunch of b vectors coming in at different times. Then you want to store LU. But if you just need to do it once, you could just do this where you have a bunch of b vectors. I guess because row reduction leaves it upper triangular in echelon form. So then you have so you have a. Wait, these are the same. What? But okay, anyways, the point is the value of LU makes sense. The reason why you want to do it is because you basically want to store for later use the factorized matrix. Now, how do we? Now, I don't understand how to actually solve AX equal to B using the LU. I don't understand this part about this. So I get how we get IY, but the backwards phase. Okay, so here's something. To find x requires 28 arithmetic operations, excluding the cost of finding. They end up being the same because elimination on AB, the augmented matrix, is identical to factor A equal to LU plus doing Ly equal B and UX equal Y. Okay. So then how do you... Okay, then the way that you get Y is you do L, B, and you row reduce to I, Y. That sort of makes sense. Then what do you do for the UY? Then for UY, UX, the backward phase of row reduction requires 4 divisions. So you start with UY. Because U times X is equal to Y. So we want to solve U, Y, and row reduce to I, X. Okay. That sort of makes sense. Okay, wait. So, but the advantage... Okay. All right. Okay. Yeah. No, you do save time. That's what I was thinking. You definitely do save time if you write it. If you write it down. But the thing is, you can do okay. That checks out. Okay, so now we know... Now let's do this. Let's say we have like a rand 4x4 matrix. Can we do a LU? Is it that? What does it return? It returns a struct. Oh. Wait, hold on. So it has what? Okay, so the LU decomposition in Julia actually has 4 things in it. It has a permutation thing, which is probably to keep the condition number low. Then it has this permutation vector, I guess. So then it probably does like a P times L times U. Maybe it does a LU times P. I'm not sure how it does it, but now how do we do like oh, okay, so there's a high level factorize. Since A is not Hermitian, symmetric, triangular, or tridiagonal, or bidiagonal, and LU, that's pretty cool. Yeah, if a matrix is known to have certain properties, then it doesn't have to do all the checking. That's fine. So, but when you do a back solve, I don't think that that necessarily does. You know what I think you have to do? I can probably do this. So let's say we have like a B is equal to rand 4. We can probably do, yeah, my lu backslash B. And that this takes 2n squared time because it knows that it's LU. So now if I get another B, you know, B2, then I can, you know, I can backslash this one to, or, okay, so that checks out. So I understand how this works now. All right. So that is actually pretty sweet. I feel like a lot of mystery has been removed from my mind because I never really looked into what the hell LU factorization was. But it's like pretty basic. You basically just write down the step. And okay, we didn't actually go through it. This video is amazing. This is the video that I watched. And basically what you do, by the way, this guy rules, bright side of mathematics. But you basically just take IA and you reduce it to LU. I mean, that's pretty much what it is. And all you do is you write down in the lower triangular part what coefficients cause this lower triangular part in A to go to 0. So, we're going to have like, let's see, let's watch him do the first part. So he's going to have -4 minus -2. And that's going to cause this. And then he's going to write it down right here. So he's going to write down that coefficient -2. And then he does that. And then when you get to the second part, don't use the top row. You want to always use the diagonal. One thing that's interesting though is this is the guy that came up with LU. When you here they just so happened that it was ones. But in this guy's, it doesn't have to be ones on the see how oh no, the L definitely has to have ones on the diagonal, but the U does not need ones on the diagonal because we're not starting it off as the identity. Okay, I'm convinced. LU factorization is pretty sweet. The thing that's kind of interesting is that when we looked at the documentation for a real linear algebra package, they do checks to see if it's symmetric before they factorize it. Well, I guess what I'm getting at is that the cost that it takes to detect whether something is symmetric or something has got to be less than the improvement. So maybe it's O of n to determine whether or not it has special properties, or maybe it's, and even it couldn't be n squared, but n log n to determine some properties of the matrix. Okay. All right. So let's probably start. Okay. So the algorithm reduce A to U, place the entries in the same sequence of row. Okay. Yeah. So we have. Okay. Yes, you get the row operations. All right. So find an LU. All right. We could work through this. I'll do it. This is a big matrix, man. Wait, I think that this is the same example that he did here. Is it not? Oh, it's close though. Okay. So I'll just write it down. So what you're gonna get is so we're gonna get like -4 to 6. So or -4, 2, and 6, and then we have a 2 up here. So -4 minus 2x is equal to 0. So x equals -2. So then you're going to put a minus 2 there. Then 2 minus 2x equals 0. Then you're going to get 1 there. Then for 6, 6 minus 2x equals 0. Minus 6. So then x equals minus 3. Okay, hold on. So, let's just read it. So, compare the first columns of A and L. The row operations that create zeros in the first column of A will also create zeros in the first column of L. Oh, that's true, huh? To make this same correspondence of row operations on A hold for the rest of L, watch a row reduction of A to an echelon form U. That is, highlight the entries in each that are used to determine the sequence of row operations that transform A into U. Wait, so what happened there, though? Oh, okay. Because this canceled both of these zeros. So you just moved to the next one, I guess. Wait, so then what do you... So, but in the L, you just skip it, right? Okay, so the important thing is, though, that you have to skip... Oh, wow, we're already... Oh, no. Okay. Okay, so that was the decomposition. In practical work, row interchanges are nearly always needed because partial pivoting is used for high accuracy. To handle row interchange, the LU factorization above can be easily modified to produce an L that is permuted lower triangular, in the sense that a rearrangement of the rows of L can make L lower triangular. The resulting permuted LU factorization solves AX equal B in the same way as before, except that the reduction LB to IY follows the order of the pivots in L from left to right, starting with the pivot in the first column. I don't know what that means. Numerical notes. The following operation counts apply to an n by n dense matrix with n greater than 30. Computing an LU factorization of A takes about 2/3 n cubed. And inverting a matrix takes 2n cubed. Solving Ly equal to B and Ux equal to Y is 2n squared, because any n by n triangular system can be solved in n squared steps. Multiplication of B by A squared takes 2n squared. Why is that? If we have an n by n times an n by 1, you're going to have to do that's n squared. So then, A inverse B is like 2n cubed plus, I don't know why it's 2n squared, but anyways, if A is sparse, then LU may be sparse too, whereas A inverse is likely to be dense. Oh, that's interesting. I like that note. That's cool. If A is sparse, then A inverse usually not sparse. But LU is. Okay, that's cool. All right. So, matrix factorization in electrical engineering. Matrix factorization is intimately related to the problem of constructing an electrical network with specified properties. The following discussion gives a glimpse of the connection between factorization and circuit design. Suppose the box in figure 3 represents some sort of electric circuit with an input and output. Record the input voltage and current. Record the output voltage by output voltage and current. Frequently, the transformation is linear, and there's a transfer matrix. The right circuit is a shunt. Compute the transfer matrix of the ladder network. You just multiply those matrices. Design a ladder network whose transfer matrix is okay. Let A1 and A2 be the transfer matrices. Then the input vector is transformed Okay, just note that it's A2, A1. To factor the matrix into the product of transfer matrices. I mean, it doesn't have to be upper and lower triangular, right? Okay. A network transfer matrix summarizes the input-output behavior, the design specifications of the network without reference to the interior circuits. To physically build a network with specified properties, an engineer first determines if such a network can be constructed. Then the engineer tries to factor the transfer matrix into matrices corresponding to smaller circuits that perhaps are already manufactured and ready for assembly. That's kind of cool. In the common case of alternating current, the entries in the transfer matrix are usually rational complex valued functions. Whoa. The standard problem is to find a minimal realization that uses the smallest number of electrical components. Pretty cool. All right. Okay, this is going to be a good practice problem. Holy shit. 2 minus 4 minus 2, 3. 6 minus 9 minus 5, 8. 2 minus 7 minus 3, 9. 4 minus 2 minus 2 minus 1 minus 6, 3, 3, 4. So L is going to be 5 by 5. So we're going to start out with 1, 2, 3, 4, 5. So this is a 5 by 4. So then U is going to be 5 by 4. So L is 5 by 5, U is 5 by 4. So for the first one, it's going to be 6. So 6 minus 2 times x is 3. So we're going to put a 3 there. Then this is going to be 1. Then 2. And then minus 6. This is going to be minus 3. But we need to rewrite the row, right? Because it's going to be R2 is equal to R2 minus 3R1, which is equal to 2, it's going to be 6 minus 12 minus 6, 9. plus 6 minus 9. So then we're going to get 0, 3, 1, minus 1. So this is R2. Oh, shoot. So it's going to be like minus 7 minus 3x equals 0. So we need to do minus 3 over 7. There's 7 over 3. I already feel like I messed this up. All right, but let's just keep going. Oh, because you know what I didn't do? I didn't apply the, yeah, wait. No, yeah, so what we need to do is we need to okay, then the third column is 2 minus 7 minus 3, 9 plus minus 2, 4, 2, minus 3. So we're going to get 0, minus 3, minus 1, 6. 0, minus 3, minus 1, 6. Is that correct? 0, minus 3, minus 1, 6. Okay. Then we need to do the next. The next one is a 2. So it's going to be R3, which is 2, or R4, sorry. R4, which is 4 minus 2 minus 2 minus 1 minus, and it's going to be 2 times minus 2 times, hold on, let me just write out the actual row operation. So it's going to be R4 is equal to R4 minus 2 times R1. So this is going to be R4, 4 minus 2 minus 2 minus 1 minus 2 times R1. So this is going to be plus minus 4, 8, 4, minus 6. So we get 0, 6, 2, minus 7. Yep. 0, 6, 2, minus 7. And then the last one is going to be R5 is equal to R5 minus 3 times R1. So we're going to get R5, which is minus 6, 3, 3, 4, plus 6, minus 12, minus 6, 9. 0, then the sum, 0, minus 9, minus 3, 13. 0 minus 9 minus 3, 13. Wow, this is so much work. Holy cow. Okay, but we should just keep doing it because otherwise I'm not going to know what the hell is going on. So then we're going to get minus 3 times x is equal to 0. All right, so our L is now 1, 1, 1, 1, 1. And then we have on the first column 1, 3, 1, 2, minus 3. Then on the second column, we're going to have a 1, a minus 1, 2, and minus 3. So now we need to compute all of those. Right, so now we need to do... So we're right here, right now. So now we need to reduce that. So, okay, so the second thing is now we have A2 operations, and we're going to get R3 is equal to R3 minus R2. So we're going to get minus 3 minus 1, 6, minus 3, 1, minus 1. So we're going to get 0, minus 2, 5. What? How did I do that wrong? The 3... Okay. So now I got it. So it's going to be 0, 0, 5. So that is okay. Okay, so you're going to get 0, 0, 5, 0, 0. Oh, because I didn't multiply it by 2. Minus 5. Okay, that's okay. Finally, I've computed this third matrix. All right. So the first step here is we want to solve Ly equal to b. So what we're going to do is and then we're going to augment this with b, which is minus 7, 5, 2. Then we're going to do R2. And this is going to be equal to 0, 1, 0, minus 2. And we're also going to do R3. Wait. No, it's just going to be 2. Minus 2, 0, 0. Wait, so wait. Dude, the minus signs always really mess me up. Okay, so what we should get right now is 1, 0, 0, minus 7. 0, 1, 0, minus 2. And then we get, so then we're going to do so what we're going to get is 1, 0, 0, minus 7. 0, 1, 0, minus 2. 0, 0, 1, 6. So y is equal to now what we want is to do u 3, 7, minus 2. And that we're going to do u y. So wait, what do we do now? Okay, so now we just need to remove this. So it's just going to be so then what does that mean? That means that we have 3, 0, 0, 19, 0, minus 2, 0, 4, and 0, 0, 1, 6. So this means that the solution vector for this means that x equals 19 over 3 minus 2 and 6. I don't know if that's correct. Okay, so y, we got y correct, but then we got u wrong. Wait, how the hell did that happen? Oh, this is a -1. Damn it. Okay, that's what messed it all up. So this is a -1. So then this is a -1. Or wait, no, this is a 1. This is a -1. This is u. So I think that this is -8. What's going on, Focus Hub? So if this is -8, hold on. I still think it's wrong because what did we have? We had -2x2 minus 1 times -6. So this is going to be -2 is equal to -2. So we have -2x2 plus 6 equals -2. So then -2x2 is equal to -8. x2 is equal to 4. Okay, so that seems right. All right, so what's the last step? What did I mess up on here? So I'll just do it right here. So now we have 3, 7, 0, 5, 0, minus 2, 0, minus 8, and then 0, 0, minus 1, 6. So we need to do 3, 7, 0, 5 plus 0, minus 7, 0. And then this is going to be minus 8 times 7 over 2, which is equal to 56 over 2, which is equal to 28. So this should be minus 28. So then we're going to get 3, 0, 0, minus 23. That doesn't sound right. Oh, you know why? Oh, yeah, because down here, this needs to be minus 12. So then this is minus 19. So then this is minus 19. Right? So then we're going to get minus 19. Wait. Oh, God. I can't believe this is taking me so long. Okay, wait. Let's just go from here. So we have y in the is equal to minus 7, minus 2, and 6. U is equal to 3, minus 7, minus 2, 0, minus 2, 1, 0, 0, minus 1. All right, so let's just say that this is minus 7, minus 2, 6. All right, so let's just do it like logically. We obviously have x3 is equal to minus 6. So then if we write this as an equation, we're going to get minus 2x2 plus 6 is equal to minus 2. So then minus 2x2 is equal to minus 8. X2 equals 4. So now we're going to have 3x1 minus 7 times 4 minus 2 times minus 6 is equal to minus 7. So 3x1 minus 28 plus 12 equals minus 7. So then x is equal to 3, 4 minus 6. Gosh, doing those by hand is brutal. Did you get it right, though? Okay, so that's correct. But holy hell, that's so bad. Okay, now it's saying also do it by ordinary row reduction. So let's try it with ordinary row reduction. So the matrix is going to be 3 minus 7 minus 2 minus 7. minus 3, 5, 1, 5, 6, minus 4, 0, 2. Okay, so we're just going to reduce this. So we're going to first do R2 is equal to R2 plus R1. So we're going to get for R2 is equal to 0, minus 2, minus 1, minus 2. Okay, then we're going to do R3. R3 is equal to R3 minus 2R1. It's going to be 0. Then we're going to get, here, we'll do this. 6 minus 4, 0, 2, plus minus 6, 14, 4, 14. So 0, 10, 4, 16. So this is R3. Okay, then what is our matrix now? It's 3 minus 7 minus 2 minus 7, 0, minus 2 minus 1 minus 2, 0, 10, 4, 16. Okay. Bro, this stuff is so boring. So now we're going to get R3 plus 5R2. It's going to be R3 is equal to 0, 0, minus 1, 6. All right, whatever. We did the most. We did most of it. Okay, what's the next stuff? So what is this? What does actually explain the backslash? Huh. Okay. These proof ones may be good. I don't know. Suppose A equals BC, B is invertible. Show that any sequence of row operations that reduces B to I also reduces A to C. Okay, so let's say we had A equals B, C, so this is 21. B is invertible, and then we want to show that the row ops that go from B to I also goes from A to C. Okay, so let B inverse equal the row ops. Then if we multiply both sides on the left by B inverse, we get A, or B inverse A is equal to C. Okay. So yeah, so my answer is that since we know B is invertible, and there's a sequence of row operations that reduces B to I, then you can write those elementary row operations as a single matrix as the product of all of the elementary ones. So then you have B inverse B is equal to I. Now, if you multiply that on the left, you get B inverse A is equal to C. But is that the same operations? Okay, so this is what I was saying. Yeah. Okay. That's a good one. Um This one seems pretty good. Show that A is the sum of four outer products if it can be written as in this way. Oh yeah, so if it's low rank, you can do because 1600 plus 400 is 2000, but wait, what? 400 by 4. Oh, so it's yeah. So it is you save 2000 numbers in B. I would like to show this though. A seems like a very good problem. Okay, QR factorization. Suppose A equals QR where Q and R are n by n. R is invertible and upper triangular. And Q has the property that its product with its transpose is the identity. '24 definitely. All right, so the problems I want to do are I don't really want to do any of these calculation ones. They're really boring. I want to do 23, 24. Suppose A is equal to U times D times V transpose. With the property that these both have this property that's product with its transpose is the identity, and where D is diagonal. Show A is invertible. Okay, 25 seems cool. Where P is some invertible 3 by 3 and D is the diagonal matrix. '26 seems cool. I don't actually care about these. I don't know. Maybe I should, but I don't really care about these electrical circuit ones. Okay, so let's just do 23 through 26. All the other stuff is applied, and I don't really care. Okay. So 23 through 26. Okay. Now the problem is show so this is the outer product. So the sum of four outer products. I mean, is it not going to be like C1, like C1? This is going to be m by 1 times d1. So this is going to be the first call, and this is going to be the first row. I think that's might be right. So this is going to be, yeah, m by 1. This is going to be 1 by n. If we were just going to go full, like, symbolic, and do, like, let's say m is 3 and n is 3 as well. And instead of 4, it's 2. Let's say this is C, and D is 2 by 3. A, B, C, G, H, I, J, K, L. So then if we were to compute the first one here, we would get ACE times GHI. That's going to be equal to AGAHAI Now, if we were to have had this, so if we were to compute the full matrix product, then this would be AG plus BJ. So if we were to do the second one would be BDF JKL, which is equal to, and this first element is going to be BJ. So anyways, the point is that these outer products, you can sum them and you're going to get the full matrix product. So I think we've shown this problem correctly. So suppose A is n by n, and A is equal to CD, and you can decompose it into this n by 4 and 4 by n. Okay, this problem is pretty cool because you can think of like a low rank factorization or something like that. And then the second problem is B. If m equals 400 and n equals 100, show why you want to store C and D, not A. And the idea is that if you have a 400 by 4 matrix and a 100 4 by 100 matrix, you're going to get 2,000 numbers that you need to numbers to store. Whereas A is 400 by 100, which is equal to 4,000 numbers. So you save half your memory. Okay, so that concludes problem 23. Problem 24. QR factorization. Suppose A is equal to QR, where Q and R are both n by n. R is invertible and upper trie. And Q has that Q transpose Q is equal to the identity. Now we want to show for all B in Rn, there's a unique, or AX equal to B has a unique solution. My lighting has gotten kind of bad. And the rest of the question is, what computation with Q and R produce solution x. Okay, so the first thing that I want to do is just figure out the substitution. So if we do QR x is equal to b. So we're not given that A spans the codomain. So technically we do need to prove that. And so the first thing that I have the instinct to do is just multiply by Q transpose. So we're going to get Q transpose QRX is equal to Q transpose B. Now this is going to cancel out and you're going to get RX is equal to Q transpose B. Now we know that, now I don't know if the fact that it's upper triangular matters, but what I'm going to do now is multiply by R inverse. And we're going to get R inverse Rx is equal to R inverse Q transpose B. And this is going to cancel out, and then we're going to get X is equal to R inverse Q transpose B. So that shows, I don't know if that proves that we have the span. I mean, for any B, we can compute X. And we did only valid operations. So I think that this is a correct derivation and proof that we span the codomain. But I am going to ask. So I guess one thing that I didn't mention, though, is that if Q transpose Q is equal to the identity, then this also implies that that Q transpose equals Q inverse. Okay. So that concludes 24. 25. Okay, this is the SVD problem. Suppose A is equal to U dV transpose. U, V are n by n. So D also has to be n by n, right? So, and we also have that U transpose U equals I, and V transpose V equals I. And D is diagonal. And the diagonal has sigma 1 to sigma n. Positive. All right. The problem is show a invertible and make a formula. Okay. For A inverse. Okay, so my general strategy on this is going to be we are going to compute U V or wait U D V transpose inverse. Okay, so we already know. Okay, so here's the thing. We know all of U, V, and D are invertible because, first off, if U transpose U equals I, then U transpose is equal to U inverse. And same for V. And then D is invertible because it's positive diagonal entries. So then we can just take U, D, V transpose inverse equal to, and this should be V transpose inverse times D inverse times U inverse. So now this is going to be equal to V transpose inverse is just going to be V. So we're going to get V D inverse U transpose. So this is what this is equal to A inverse. So that was actually a really easy problem. Yep, that's all you had to do. Pretty simple. Okay, the last one. This one I was actually really excited for. 26. Suppose A 3 by 3 and A is equal to P D P inverse, where P invertible and D is diagonal with D equal to 1 0 0 0 1 half 0 0 0 1 third. Okay, we want to show this factorization is useful for computing a to the n. Okay, so the first thing we're going to do is let's just take a squared is going to be equal to P D P inverse times P D P inverse. Okay, so this should be obvious because we basically see immediately that this is going to be equal to P D P inverse P D P inverse. Okay, so the point is that this middle part is going to cancel out. So then if we want to compute a to the k, basically all we have to do is compute let's see. Is this true? Actually, is a b to the n equal to a to the n b to the n? How do we prove that? I don't know if that's true. But if it is true, then the formula is going to be p to the k, d to the k, p inverse to the k. And what's nice about this is going to be fast. And I don't know about the outsides. So wait, we need to check though. Yeah, I am reading the comments. What's up, Weary Adventurer? I am most definitely reading the comments. Okay, so wait, we need to prove that for matrices. I don't actually think that's true. So I don't know if we can do this. I mean, it's certainly true that it actually it might not look like this. It might look like P. Let's see. Oh, it's gonna be P d squared P inverse to the k. I think that this is the formula. I don't think because the thing is, imagine that A is m by n and B is n by k. Well, first off, this power is not going to work. But even if it's n by n, I don't think that matrix power. Well, okay. Okay, so let's just double check. For matrices, is AB to the n equal to A to the n times B to the n? And I'm almost certain it's not because it doesn't. Yeah, yeah. It would only matter if it would only work if it was commutative. Yeah, so this is the actual formula. So I think. Wait. But that's the thing about this is that if you did this, you would get another one to cancel. So I got to think about this. Yeah, I'll be right back. Okay, so clearly we have um, that the inner things here cancel out. So let's just try 3. Why not? PDP inverse times PDP inverse times PDP inverse. So we're going to get these cancel and these cancel. Oh, so no, you know what I think it is? I think it's just equal to P d to the k P inverse. I think that that's all you have to do. So then, and computing this is easy, and you don't even have to compute powers of these. All right, so this is what a to the k is. So that is the answer right there. So the reason why this is advantageous is that so the thing that's annoying about this though is that it doesn't, like, do you always get this factorization, or is it only certain types of matrices that admit this factorization? That's what the book is not telling me. I don't know. Maybe it is, maybe it isn't. Anyways, so there we go. That's 26. And I think that that's all I'm doing for this section. I'm not going to do any of the applied problems. We could just move on to 2.6, but I'm going to make it another stream, but I think we're going to end this one. So this one was good. I actually kind of like these factorizations. They're pretty fun. Okay, peace.